Hi, everybody. Steve said I'm Megan Frye. I work for Federal Lands, for FHWA at Central Federal Lands. And just to start out the presentation, soliciting a little bit, we're going to be hiring soon. So if you've seen the cool work that we do at Federal Lands, check out USA Jobs and come work for us. I have 2 positions open, so more to come on that. I'm here to talk to you today about some of the benefits we realized using a 2-dimensional hydraulic model for enhanced collaboration. Really helped to streamline environmental and engineering activities on a previous project. And near the end of the presentation, I'll go through the project that we used 2D modeling on and how it really helped in the permitting process. So first, let's talk a little bit about some of the advantages of 2D modeling. And you probably feel like we're really hammering this into you, but I think 2D hydraulic modeling is awesome. And we've realized so many great opportunities with 2D modeling that weren't available to us with 1D. So we have fully adopted it at Federal Lands and don't plan on going back, ever, hopefully. Just a couple of them that I wanted to cover. 2D hydraulic modeling really helps improve quality and resiliency. I think we've really realized how much a 2D model is a better representation of that complex interaction in the river environment and transportation assets, and I think that's really helped us a lot in our decision-making process and just overall making better decisions in project delivery. Probably my favorite part of 2D modeling, the enhanced collaboration opportunities we have with visualization in 2D modeling. I threw in a couple pictures here you can't really see, but that's a group of us out in the field, and everybody has a printout from a 2D model that I developed. And we're at a bridge, and we're talking through design parameters and design conditions, flow conditions, and that kind of stuff isn't possible without these awesome visualization tools. And those 2 basically roll into streamlined project delivery. So I think, in my opinion, those are really the big advantages in 2D modeling that I want to highlight. So let's talk a little bit about our opportunities for enhanced collaboration. I threw up a couple of projects that I'm looking forward to using these on, and projects we've used 2D modeling on in the past that have really, that we've really benefited from the visualizations. I am really looking forward to, I haven't done an aquatic organism passage design with 2D yet, but I think the opportunities to really map out the flow distribution, areas of high and low velocity, areas of deep pools, shallow pools, differing shear stresses, I think will give us a really great chance to come up with a much more informed design for aquatic organisms. The second is kind of a combination of river training and wetland restoration. That's an example on the right of a project that we completed at CFL. The top picture is the existing condition, and you can kind of see this is for a 10-year flow. There's this little chunk of wetland near the top of the picture that you can see is almost completely abandoned. It's not getting any flow. Results of a flood and a couple of other conditions. But really the purpose of the project was to find a way to get that flow back into the wetland without a real complex stream restoration or channel rebuilding, just something light and simple using the materials we had out there. So the bottom picture is the proposed condition with just a little boulder weir I was able to put into SMS. It's kind of close to the little yellow pocket of flow. And we were able to really take that to the partner agencies and say, here are your existing conditions and here's what we're proposing and how that'll change your flow conditions. Just a great tool for communication. And the remainder of the presentation will really be about how we were able to use 2D modeling to identify the ordinary high water mark, which, as you all know, is important for permitting under the Clean Water Act. So we'll dive right into the project overview. It is a bridge project approximately 50 miles south of Albuquerque, New Mexico. The scope of the project is, so basically we have this existing bridge was built in the 1930s and has been deemed structurally deficient. So because of the historic nature of the bridge, the scope is really to build a new bridge immediately upstream of the existing bridge. And as a part of all of that work, we needed to identify the ordinary high water mark for waters of the U.S. and to streamline our permitting process. So let's talk a little bit about ordinary high water. And ordinary high water in the arid West is a tricky thing. So for those that don't know, the ordinary high water mark demarcates the lateral extent of the federal jurisdiction of waters of the U.S. And waters of the U.S. are basically what you need to apply your permits for under. It's basically any like fill or work within waters of the U.S. needs to be permitted. Our current delineation methods is basically just field indicators. We use this field guide generated by the Army Corps that's specific to the arid West. But something that they bring up within this field guide is you get a lot of conflicting field indicators in the arid West, and it makes it really difficult to identify those jurisdictional limits. So if you go into a different publication by the Army Corps, they talk a lot about how your flow characteristics and hydraulic modeling can be used to help in the delineation beyond just the information that you collect out in the field. So that's really what we wanted to hone in on this project. We wanted to first go out into the field and survey, pick up all those field indicators for ordinary high water, and then come up with a final true delineation for our permitting. So this gives you, excuse me, overview of the field indicators. So basically, our environmental specialist goes out and gathers field data for a day or two around the bridge location, and he's looking for basically 3 categories of field indicators. He's looking for breaks in slope, changes in vegetation, and changes in sediment type, size, etc. So this is our bridge site. Flow is from top to bottom, top to bottom. The bridge, you can see the existing bridge is kind of right there in the middle. And that first line upstream of field indicators is more or less where our proposed bridge is going to go. And from this map, you can kind of see that our field indicators are all over the board. They're basically contained within that floodplain, but we could pick any number of those dots to draw our ordinary high water mark, and the problem really becomes what do we use, right? So that's the pickle we're in right now. Just to give you, this is kind of to showcase the SMS tools, but also to give you a better idea of what the site actually looks like. This is an oblique view of, we're upstream of the bridge looking downstream with the field indicators mapped on there. And as you can tell, it's a pretty deep incised channel with a couple of terraces, a pretty wide floodplain, and then you get up into this overland that's basically just flat desert. So if we focus in, there's kind of a berm just immediately upstream of the bridge on the right-hand side of the channel. So if you focus on those field indicators that are right around that berm, here is a photo of the site. We're upstream of the bridge, looking downstream at the lovely existing bridge. And you can see pretty clearly there's like a very well-defined incised channel, pretty clearly defined breaks in slope for terraces and floodplains, and then a pretty obvious transition from grasses and pretty common bank material to a more well-established floodplain material. Actually, a lot of the vegetation at this site is tamarisk, which is an invasive floodplain or wetland plant, which presents its own issues. But what I really want to highlight here is you could pick any number of those field indicators that we surveyed for ordinary high water, and they would all be representative of what's out there, but what is the true ordinary high water? Is it that first terrace? Is it that first line in vegetation? You can kind of tell. I don't know if it's hard to tell in the bigger picture, but you can tell the change in vegetation by there's kind of a change in the color of the sediment to the left of the channel. So it presents this problem of what do we choose? And is it an informed decision, or is it a decision we're making to better fit our project and to streamline our permit? So those were the issues we were facing. This is a prettier picture of the same view in the springtime, so with the trees and vegetation's actually blooming in color. And that low flow is pretty typical of this site. I think every time I've been out there, there's been little to no water in the channel, so just a FYI. One more view to get you fully into the site. This is from downstream, looking upstream at the bridge. We'll focus in on that first line of field indicators just downstream of the bridge. So basically, again, we're looking for breaks in slope, changes in sedimentation, changes in vegetation, immediately downstream of the bridge. And we're seeing pretty much the same conditions as we had upstream, that deeply incised channel, terraces, and floodplain. And the same issue we're having of what is our true ordinary high water. So that leads us to the first graphic we put together of some basically draft ordinary high water delineations. So the question really became, do we pick just a line that connects all of the changes in sediment maps, or do we pick the breaks in slope? Do we pick a combination of all three? And the permitting impacts for this delineation are, they're pretty big. So we really wanted to be able to go to the core with the true representation of what the ordinary high water was at this site. And that's where I get to come into the picture. So as a hydraulic engineer, I had already put together a hydraulic model for this site to do all of the computations I would need to do for a proposed bridge. So it didn't take much with a 2D model for me just to put in a couple more flow conditions for us to consider for ordinary high water. Just a real brief overview of the model. It's about 26,000 elements, size varying from like 1 foot to 250 feet in length, and the model runtime is about 12 minutes. Some more variables that aren't up here. I had a combination of LiDAR and ground survey that I used for scatter data, and had the benefit of having a gauging station in the vicinity of the bridge, as well as a very recent flood with a fair amount of observation and data recorded within the vicinity of the bridge. So all of that information was used to calibrate the model. And I guess full disclosure, this was one of the first 2D models I put together, and I went over the top with the number of elements. I don't know, inexperienced, and I was kind of excited, and I don't know, 12 minutes is enough time to like get up and stretch your legs and then get a cup of coffee, and that seemed good enough for me. So probably now I would do something a little different, but as you can see from the picture, it is a pretty complex mesh. But 12 minutes, that's not that much, right? All right, so let's dive into the results of the model. So with discussions with the environmental specialists, we decided we wanted to look at basically two flow conditions. So we were looking for some correlation between the field indicators and the output from the hydraulic model. So we looked at the 2-year and the 5-year, and we're hoping that it would fall somewhere between there, and we would somehow be able to correlate what we were seeing in the field with a final ordinary high water delineation. So this is just pretty self-explanatory. You can see the deep flows within the main channel itself. I think at its deepest, it's flowing at about 10 feet. And it's also pretty obvious that this channel accesses its terraces and floodplains pretty regularly. So ordinary high water, that basically follows the main channel was thrown out the window pretty quickly. So depth visualization with the field indicators mapped on top. And like I said, we're really looking for a correlation between the two. So we were pretty happy with the results of the breaks in slope were pretty obviously lining up with the big changes in flow depth, which is what you would expect. We were also pretty happy to see the extents of the 2-year flow lining up pretty well with the changes in vegetation that we see on the outer edge of the floodplain. And then it's a little more indicative in the 5-year model, but you can kind of tell the areas where we had deeper pools and slower velocities were also where we were seeing our big changes in sediment. So right out of the gate, we were pretty happy with like, well, a 2-year looks pretty representative of what an ordinary high water would be at this site. To follow that up, we looked at velocities also. Because it's so much different, the plot is so much different, I cut the velocity off at 0.1 feet per second because I feel like anything below that's kind of irrelevant to a velocity profile. So again, we can see that with our field indicators mapped on top. And really, again, we're just looking for correlation. So this is a little less, we were a little less happy with how this was correlating, especially, just upstream of the bridge, which would be to the left of the screen. We have some field indicators that, aren't showing any significant or measurable velocities. And there are other areas along the outside that are lining up, but we weren't 100% satisfied with the 2-year flow and how it was lining up with our field indicators. So we moved on to the 5-year, and this is the flow depth visualization again. I kept the scale the same, so you can see that a significant amount of water now is making it out of the channel into the floodplain, really pooling in those depressions in the floodplain just on the left side of the bridge. And with the field indicators, we can see, again, that upstream of the bridge, we were pretty happy with the correlation of, again, it was lining up really well with the changes in vegetation, lining up pretty well with the breaks in slope. But once we moved downstream of the bridge, we started to see a lot more flow outside of the floodplain and into the overland that we didn't really think was indicative of the ordinary high water, and we're a little more confident that the field indicators were a better representation of the ordinary high water mark out there than what we were seeing with the 5-year. And that's true as well with velocity. Again, we were really happy with how well they were correlating upstream. So like I said before, we were seeing changes in sediment where we were having deep water, slower velocities, changes in vegetation at the extent of the flow, all of the things that we were really looking for as a truth, basically, for the field indicators that we'd mapped. And downstream, it was kind of the same. It's a lot of water outside of the floodplain and probably not representative of ordinary high water at this site. So our final consensus was, at this site, it's probably somewhere between a 2-year and a 5-year, depending on where you are within the cross-section, within the floodplain. But the true ordinary high water mark is going to be somewhere in between. So, ta-da, this is our final ordinary high water delineation. I'm sorry, I can't see it. It looked weird from over here. So we can see, if you can remember back to all of the, the flow distributions for the 2 and 5-year, it's a pretty good mix between both, mostly 2-year, but downstream of the bridge, it followed more along with the 2-year, mostly the 5-year upstream and 2-year downstream. Sorry. So this was our final result. This was the culmination of a lot of back and forth with the environmental specialists and I to come up with our true final delineation. So to kind of wrap it up, I just wanted to highlight a couple of the opportunities that we realized on this project and that we're definitely going to be looking for moving forward on projects at CFL. The first really was internal collaboration. We actually have the environmental specialist is pretty excited about SMS and 2D modeling, so he has a version on his computer and likes to create visualizations. And just that communication back and forth has been really beneficial and has really helped us streamline our decision-making and collaboration really across the cross-functional team. It also really helped in communication with project stakeholders. This has been true on this specific project as well as a lot of previous projects. It's a lot easier to communicate with folks who are familiar with the site when you can come out with 3D visualizations where they actually feel like they're at the site and they're familiar with the landmarks, and you can superimpose modeling results on top of that, and they really get the picture. And it just helps all around with collaboration. And really the final was what I just highlighted. We got some questions from the Army Corps. The environmental specialist got some questions on how he delineated ordinary high water for this specific project, and he was really able to walk them through this full process, and they were pretty happy with the results. And it was one question, and they moved on, and we got our permit approved. So, all in all, a success. And that's it for me. Any questions? Time for questions? I see I went 21 minutes and 49 seconds.
I did have a question. Did you ever any thought to try to maybe put a meter or an aerial meter on a bridge to see and calibrate that for the final results with a rain gauge or a sensor?
It's not something we'd ever, with our projects, it's a lot of like, you come in, design it, and go out. We don't own or maintain any of our sites, so I was pretty excited to have gauge data. That's pretty uncommon, but that would be I was amazed just at how easy it was to calibrate the model with that gauge data. So I'm sure, if you could get real-time data to calibrate your model like at the bridge itself, that would be amazing.
Thank you.
Yeah.